even though in a steady flow system you have mass flowing in, it doesn't necessarily carry with it all three of these energies. Sure, that mass has enthalpy, likely, unless there is no mass, in which case it's not a mass flow problem. It likely has kinetic energy because it's flowing. So it likely has a velocity, and kinetic energy is the energy of velocity of something that has mass moving. So it's likely going to have an impact in the terms of kinetic energy. But it won't necessarily have a potential energy term. And just like we think about velocity with kinetic energy, we always think about height with potential energy. Potential energy is the difference in height from one height to another height and the effect of gravity on that mass going from that one height to another height. But if I look at this problem, the mass is coming in at, say, this height, and the mass is going out at this height. The type of problem that would have a mass flow that has potential energy would be something like this. If the inlet and the outlet have literally different heights. So if this is height in and this is height out, and we measure it from a constant, this would be H1, this is H2, and there is a delta H between them. That's going to be the case where we would, yes, have potential energy. This is the energy potential case. But in the case that I showed up here, there is no difference in height, so mass would be crossed out. There's also opportunities to simplify this equation. Of course, the final equation ends up being this. It's saying that the change in internal energy of the system is the difference in heat energy, plus the difference in work energy, plus the difference between mass flow. That's not going to be the case for all problems, because you might have a problem where no heat is added, in which case, and no heat is removed, in which case you get rid of both of these. Maybe this isn't doing any work on anything, in which case you take away the work terms as well. And then maybe you take away the potential energy term from these two, and you actually have a really simplified equation. But so this is very, very basic. This is a very basic form of the equation for a first law energy balance with a steady flow and coming into and out of it. So this is a first law energy balance, a steady flow system. And all we did, this is not a new equation. It just says the energy on this side, the energy on this side has to equal the energy on this side. Internal energy that it already had, plus some heat you added if you did, plus some work that you added if you did, plus some mass came in and it has its own potential and kinetic and enthalpy, must equal the resultant internal energy, plus any heat that gets lost, plus any work that gets done. Remember, work is force times distance or pressure times volume, and plus the change in energy due to that mass flowing out. And that's how we set up a first law energy balance for a steady flow system. It is exactly the same as for a non-flow system, except it has a steady flow terms of energy due to mass flow in and out.